Let's take a look then at the total angular momentum, because then that will allow us to explain the magnetic behavior of the atom, the entire electron as a whole. Okay? So we have to take into account the angular momentum vector, L, and the spin angular momentum. So to make a distinction, we're going to call L now, from now on, instead of just simply referring to it as the angular momentum vector, we're going to call it the orbital angular momentum vector. Okay, and we're going to call S here, this is the J vector. S is going to be our spin angular momentum vector. So if the orbital angular momentum is quantized and the spin angular momentum is also quantized, then that means the total should also be quantized. Right? If there's restrictions in L, there's restrictions in S, there must also be restrictions in the total J, total angular momentum, which we're going to call J. How are we going to figure out what the allowed values of J are? The best way to do it is to keep in mind that the Z components will just add up, right? So figure out all the possible ways that you can add up the Z components of your orbital and your spin angular momentum. So figure out the allowed values of J sub Z. Okay, so if we call M sub L and M sub S the Z component, so we're going to call M sub L H bar as the Z component of L. Okay, and we're going to call M sub S H bar as the Z component of the spin vector. Okay, we look at the restrictions in M sub L and we look at the restrictions in M sub S. That will tell us what the restrictions will be for the total Z component, which is going to be 1. J sub Z is LZ plus SZ. Okay? Magnitudes of the L and the S vector are not going to add up because they're oriented in different directions. They're not going to add up to the magnitude of the J vector. But you know the Z components are going to add up. So that's what we're going to have to do to figure out the allowed values of J. All right. So let's take a look at the S orbital to make things simple. L equals 0. What's the only allowed value of M sub L here? 0. Okay. But what are the two possible values for M sub S? Plus 1/2 or negative 1/2. So what's the only allowed value of M sub J? 0 plus 1/2 is 1/2. And 0 plus negative 1/2 would be negative 1/2. In other words, what we're saying is there is no orbital angular momentum. Whatever S is, that's your J. Right? So your J here is equal to 1/2. M sub J is 1/2 and negative 1/2. Okay? So that's for an S electron in an S orbital. That's an easy one. Let's try for an electron in a P orbital. What are the possible values of M sub L? Negative 1, 0, and 1. Positive 1. What are the allowed values of M sub S? Positive 1/2 or negative 1/2. So let's make a table. So what are the allowed values of M sub J? M sub J will just be M sub L plus M sub S, right? So what is negative 1 plus 1/2? Negative 1/2. What is 0 plus 1/2? 1/2. So what I'm tabulating now in black would be the allowed values of M sub J. What about plus 1 and plus 1/2? 3/2. Negative 1 and negative 1/2? Negative 3/2. 0 and negative 1/2? Negative 1/2. Plus 1 and negative 1/2? 1/2. So those are your allowed values for M sub J. So what are the allowed values of J then? Remember, M sub J's go from J, negative J to positive J, right? So what's the largest M sub J that we have here? 3 halves. So that must be part of a set that goes from positive 3 halves to negative 3 halves. So we have one that goes from negative 3 halves to positive 3 halves. What's the other m sub j's that's part of this set? Negative 3 halves, negative 1 half, and 1 half, positive 1 half. So I can pick this one as part of that set. I can pick any of these negative 1 halves and any of these positive 1 halves. That's one set. That's one possible j. That's one of the allowed j's. J equals 3 halves. When j is 3 halves, then your m sub j can go from negative 3 halves to j equals positive 3 halves. Well, how do we account for this extra 2 here? That must correspond to the m sub j for another allowed j. What would that j be? That means j equals 1 half is also allowed. For this j, m sub j is going to be 1 half and negative 1 half. So as a result, what we're saying is if you have L equals 1, S equals 1 half, right? The allowed value of j is either 3 halves or 1 half. Okay? Sorry? Okay. Your j equals 3 halves will correspond to m sub j of 3 halves, 1 half, negative 1 half, and negative 3 halves. And j equals 1 half would correspond to m sub j of plus 1 half and negative 1 half. 6 quantum states, in other words. Okay? In other words, what we're saying is if an electron happens to be in a 2p orbital, there's actually 6 ways it can be in a 2p orbital. And that's why you've learned in your freshman chemistry. You can put 6 electrons in a 2p subshell. Okay? Because you have 3 orbitals in a p subshell. There's 2 ways an electron can be in each of those orbitals, spin up or spin down. 3 times 2 is 6. And that's what we did here. Okay? 3 possible m sub L values times 2 possible m sub S values. That gives you 6 possible m sub J values. In other words, what we're saying is the number of possible m sub J is equal to 2L plus 1, the number of possible m sub L's, times 2S plus 1, which is the number of possible m sub S. In this case, 3 times 2 would be 6. There's 6 quantum states. So the degeneracy of the P, the 2P, any P subshell, is actually 6. There's 6 ways that an electron can be in a p orbital. It can be p plus 1 spin up, p plus 1 spin down, p0 spin up, p0 spin down, p negative 1 spin up, p negative 1 spin down. Those are the 6 different ways. Okay? How are those 6 ways different? They're different in terms of their angular momentum. Okay? You can think of them in terms of m sub L and m sub S, or you can think of them in terms of J and m sub J. Okay? In fact, what's going to happen is this J and m sub J right here, okay, will actually at a higher level of accuracy for the treatment of this one electron system. Okay, when we take into account what's called spin-orbit interaction, okay, this set right here would actually be at a different energy level than that set. So that split, that 6-fold degeneracy is going to be broken when we take into account what is known as spin-orbit interaction. We'll deal with that in just a little while. So you're going to have 4 of these quantum states would be at a different energy level from the other 2 quantum states. Pauli's exclusion principle is another postulate of quantum mechanics. We're going to talk more about this when we deal with atoms with more than 1 electron. Basically says that if you use orbitals to describe more than 1 electron in an atom, then you cannot assign the same orbital end spin to 2 electrons at any given time. So no 2 electrons can be in the same orbital and have the same m sub S. Okay, so if you have You've learned this in your freshman chemistry. If you assign an electron in an orbital, if one is spin up, the other must be spin down. So you cannot have two electrons having the same set of 4 quantum numbers assigned to it. So for 2 electrons in the same orbital, what's the only allowed value of a spin angular momentum then, if that's the case? If one is spin up, the other has to be spin down. What's the possible sum of m sub s of electron 1 plus m sub s of electron 2? 0. And that's why we said that when you try to explain the silver, okay, you have all the electron. When you look at the electron configuration, all the electrons are paired except for that one outer electron. Okay, so the magnetic behavior of silver atoms basically depends on that one extra electron at the very last orbital, the 5s electron. Okay.